Okay, we left off talking about the shapes of distributions yesterday on Monday, and so if we have something that looks like this, whoops, that's terrible. What would we call this shape? Left skewed. Okay, great. And what does it mean to be left skewed? A tail on the left side, but what does it mean to have a tail on the left side? So it means, you know, if we think about like what is, quote, typical or average, okay, something around here, right? Typical values or average. So something that might be left skewed would be like scores on a test, on a, we'll say, relatively easy test. Okay, so we can have a relatively easy test, and most people score quite high, okay, but just with the nature of tests, you can't score over 100% or over the maximum, getting them all right. That's generally the max you can do. And if it's relatively easy, most people will score high. But whatever test it is, inevitably there will be a few students who score poorly. So let's say the average of the test was like 90%, okay? There might be some person who scores only 30%. 30% would be 60 points lower than 90. And if we try to go that much above, that would be out at 150. 150 would be 60 points over 90, and nobody's going to have that score. The max would be like 100, okay? So that would be something that is left skewed, okay? We would also say this is unimodal. Unimodal meaning one peak, right? We have a few other shapes. Okay, for example, we could have something that is bimodal. Okay, bimodal would be something that has two peaks. So this is, again, this is a numeric variable. All right, and I'm trying to think of an example here that is bimodal. Okay, but we could have just making something up here, which is maybe it won't look like this, but we can say, you know, how much dog food did you buy last year? Okay, and the answer to this distribution, you know, you're going to have a whole bunch of people who bought $0 of dog food, okay? All right, so you're going to have a kind of a peak there, and then you'll have people that bought at least, you know, something probably that looks something like this, all right, where this is like typical amount of dog food for a dog, one dog, okay? I don't know how much dog food costs for 1 year. And then you're going to have some people who spent a lot, right? So this will be bimodal, but right skewed. Okay, because you'll have a large peak for people who spent $0 or close to $0. And then a peak for, quote, the typical amount for a dog. And then some people have like 5 dogs or whatever, right? Okay, but you probably have more people with just 1 dog or 2 dogs, and so you're gonna have more over here. And then some people buy like really fancy dog food, right? So, you know, however much you have there. Okay. I don't know, something like that. So these would be bimodal. If you have more than 2 peaks, we might call that like multimodal. You know, how many years of schooling have you had? You know, there might be a peak for people who graduated high school, another peak for people who with 4-year degrees, and another peak for, I don't know, people with longer, more education and things like that. Okay. So this is just different shapes of numeric distributions. When we can talk about displaying categorical variables. So here I'm just kind of wrapping up chapter 2. Okay, and so with categorical variables, maybe we look at some kind of flower, colors of a flower. And we'll say the flower can come in red, pink, or white. And maybe we have 25 and 52 and 21, okay? And so when we look at this, we can create what we call a bar chart. And across the bottom of the bar chart, or across one axis of the bar chart, you have the different categories. And across the other side, you'd have the frequency. Okay, so this might be 10, 20, 30, 40, 50, and 60. And so red is at 25. Pink, we said there's 52. So that's right there. And white is at 21, so okay. So this is one group of flowers. We can have another group of flowers. Let's say we also have red, pink, and white. And so in this case, okay, all of these, they all show up with something like this, okay? And so field 1 versus field 2, so this will be flowers in field 1, and we look at flowers in field 2. Which field has more diversity or more variation in the colors of flowers? Okay, so what do you guys think? The answer is field 2 has more variation. Now, why is that? Okay, So when we look at field 2, we say it has more variation because each of these different categories are like nearly, or in this case, they're equally represented, okay? So this is the kind of the most amount of variation that we can have as far as the colors of the flowers go, okay? We can imagine a third field, okay? A third field which looks like this. Okay, what does the third field look like? All the flowers are pretty much just one color, right? I mean, there are a few pink and white flowers, but pretty much all the flowers are red, okay? So you would not look at field 3 and say there's a lot of variation here. You would say there's hardly any variation here, okay? Field 2, you have red, pink, and white all kind of equally represented, so there's a lot of variation in the color there, it's present. And then in field 1, you've got a lot of pink flowers, okay? So that decreases the amount of variation. You do have red and you do have white, but you know, if we were to kind of close our eyes and just pick some flowers at random, we've got a much higher chance of picking a pink flower, okay? And so we would say field 2 has the most variation. In this case, field 3 would have the least variation. So when it comes to categorical variables, more variation indicates that the different categories are more nearly equally represented, okay? So, you know, a topic of discussion is, you know, diversity in universities, right? And so there's, you know, there's questions about, you know, underrepresented minorities, and the complaint is that in certain institutions, you know, certain minorities are not represented well, okay? And so we would say there is less diversity or less variation at those places, whereas at institutions or universities where every group or ethnicity is nearly equally represented, we would say there is great diversity and great variation, okay? And so that can be applied to categorical variables where we are not measuring a number or something like that, okay? Okay, that pretty much wraps up what I'm going to cover in chapter 2 in lecture, and then we'll get into chapter 3 for numeric summaries. Make sure you do the relevant homework from those chapters 1 and chapters 2, and I hope that stuff is going okay. You know, if you have any questions, don't hesitate to email me or approach your TA with questions. And then you know, I've also posted the solutions to most of the homework problems that I've assigned. Okay, so check those out as well. Okay. All right, we're going to get into chapter 3. And chapter 3 is all about creating summaries for numeric variables. And so when we're talking about numeric data, okay, we can summarize our data instead of talking about the entire data table. So imagine, you know, you've gathered data from a sample. So imagine you gather data from a sample. Okay, and let's say, in your sample, we'll say n is equal to 200 observations. So, you have 200 observations in your sample, and you want to be able to describe the data that you have, okay? It would be rather inefficient to try to describe all 200 people or values or things inside your sample. And so instead, we can summarize this data with numeric summaries. Okay, so we will summarize the 200 observations with numeric summaries, okay? And we often call these, they're called statistics. Okay. And so, we're familiar with this idea here, okay? So, examples of statistics that we are already familiar with. So, you guys are familiar with the concept of a GPA, okay? Your grade point average. This is a single value, a single numeric value that's supposed to summarize your entire academic performance. Okay, and it's probably not a good idea to try to boil someone's life story into a single number, okay? And that's not a good thing to do, but it is useful to have this, right? So if we wanted to kind of get an idea of who is a high-performing student and who maybe is not as high-performing, we can look at every single class that these students have taken and look at individual grades and get a better picture, and we'll say like, oh, this student did really well in their literature classes but struggled in these classes, or this student did really well over here but or this student took a bunch of easy, like we can look at all of these things, but that's a lot of work, and it's sometimes too much information for us to make meaningful comparisons. So the GPA is supposed to simplify our lives by just saying like, oh, this person has a 3.9, this person has a 2.0, okay? And you get an idea of how one student compares to another by being able to compare just those two values, 3.9 versus 2.0, gives us an idea of the overall academic performance. It might not capture all of the stories. Maybe one student, struggled with different things or had to face different obstacles in life, and all of these are not captured. But overall, that's what statistics are. They are just summaries that, for better or worse, try to simplify our job of trying to make comparisons from one set of data to another. Okay. For example, and statistics appear very often in sports, okay? So if you guys watched the NBA Finals, there's a basketball player, and so if you don't know, there's a basketball player called Steph Curry. He had an amazing season. Okay, during the regular season, he scored many 3-pointers, broke records, like completely smashed records actually, and did all sorts of things. And then during the finals, his performance was not as good. And so rather than trying to explain to someone who doesn't know very much about basketball, like what happened during games, this game and that game, and all of these things, you can just take certain numbers and just say Steph Curry's shooting percentage during the regular season was this. He every time he tried to shoot a basket, he made it. I forget. Like his 3-point shooting percentage was almost 50% during the regular season or something like that. Whereas during the NBA Finals, it was much lower. And so those simple numeric values, those summary statistics, can summarize overall performances or just information with just easy to compare numbers there. Okay, so GPA, and then for sports we have things like points per game or shooting percentage. These are summary statistics. So summary stats for basketball. Okay, and so these are kind of tailor-made statistics for certain applications. Okay, so these statistics are quote-unquote custom-made for specific contexts. All right. It wouldn't make sense to try to calculate the GPA for a basketball player. Okay, I mean, unless that basketball player is in school and then it's not. You can't. There's no sense in trying to calculate a GPA of a NBA player who is not in school taking classes. Okay, that's it just doesn't make sense. All right, so these are all custom made for a certain context. GPA is for an academic context for students taking classes. Shooting percentage, well, that's any game where shots are taken, but for basketball it's relevant. You have passer rating for football, and you have whatever it might be. Or if we're talking about economics and the country, you often hear about the unemployment rate or the inflation rate, and these are supposed to be indicators of how well a country's economy is doing overall. Okay, of course it's just one little aspect, but they're supposed to be indicators of overall economic health or things like that. Or we can look at your cholesterol level or your blood pressure or things like that, and that gives an idea of certain stuff. Okay, so we have so those were numeric summaries or statistics for certain contexts. We have summary statistics that are useful in almost any setting with a numeric variable. Okay, and so these are, we have summary statistics that give us an idea of central tendency. So central tendency is the idea of our values, what values are typical, or what values are kind of like the average values that show up. Okay, so this is like what values are quote unquote typical. Okay, and so these values are the mean and the median. Ideas for central tendency. I guess you can throw the mode in there as well. And then we have summary statistics. For dispersion. Or spread, okay? And here it would be, are the values similar to each other, or are the values quite different? Are the numeric values in a data set similar to each other? Or are they very different? Okay, and so in this case, we would have things like the standard deviation, the range, and the interquartile range. Okay. You guys catch up there? Okay. Now, our textbook says that for symmetric data, so what does it mean to be symmetric? So symmetric means if you have extreme values that are much greater on one side, you would also expect approximately the same number of extreme values in the opposite direction. Okay? Whereas a skewed distribution means you'll have extreme values in one direction but not the other. Okay? So symmetric means you'll kind of have, whatever appears on larger than average, you'll also have similar types of things going on the low side. Okay? So things like height would be symmetric. You have some really tall people, you also have some really short people, okay? Overall, most people are average heights, okay? But then things that are skewed, you just have extreme values on one side but not the other. So you might have people who score 20% on exam where average is 90, and you're not going to have anyone who scores 160 on an exam, okay? All right, and so our book says for symmetric distributions, we might prefer to use the mean for center and the standard deviation. Okay, and then it says for skewed distributions, we may prefer to use the median and the IQR. Okay, but the truth is that you can calculate the mean, standard deviation, median, and IQR for any numeric variable. Okay. With these summary statistics, calculated for any set of numeric data, whether it is skewed or not. Okay. But it does have a point in saying the mean and standard deviation might be preferred for symmetric data, and that the median and IQR might be preferred for skewed data, because these summary statistics do exhibit certain properties that make them useful in those different situations. Okay. So if I may, I'm going to flip the slide here. Okay, so let's talk about the mean. And I think we're already familiar with the mean. The mean is often called the average value. Okay, it's also the balancing point of our data. And the way we calculate it, and the symbol that we use for it is x bar. X bar indicates the mean of a sample. And the way we calculate it is we use this symbol. This symbol means sum. We add up all of the x values and we divide by n. Okay, so sum the x's, or add them up, and divide by n. Okay? So I think you guys probably learned this in middle school or high school or something along the way. All right? And so let's say there's a family with 4 kids. Okay, and the kids' ages are 2, 4, 6, and 16. Okay? And so in this case, our x bar would be 2 plus 4 plus 6 plus 16 divided by, how many numbers do we have? 4, right? So on top we get 28. Divide that by 4. Our x bar is 7. Okay, so the mean age here is 7. Visually, we can imagine a number line here. Okay, and I'm going to just put blocks here at 2, at 4, at 6, and at 16. Okay? So imagine this thing were some kind of plank or like a seesaw. And if I wanted to have this thing balanced, okay, and these are all bricks or some kind of stone. If I wanted our seesaw to be balanced, I would put the fulcrum right here, okay? And this would be at 7. This is our mean. This is the balance point of our data. if you had to describe the shape, what would you say? Skewed left, skewed right, symmetric? Skewed right, okay? Skewed right, because we have extreme values. Okay, we have extreme value to the right, okay? And if we try to go that distance below, we don't have anything. If we think about like what is, so if we ask what is the average age here, we would have to say the mean is 7, okay? On the other hand, the median, let me the median age, the median is the halfway point. It's the spot where half of the values are larger and half of the values are smaller. So what is the median in this scenario? Yeah, so the median, we've got 4 values, and so our median here is 5. Okay, because we want, with 4 values in our data set, or in our sample, so we want the spot where 2 numbers are larger, 2 are larger, and 2 are smaller. Okay, so in this case, our median is 5. Okay, and so we can kind of see a scenario where, you know, we might say the median or the mean is preferred in a certain context here. Okay, so for example, imagine we were at a diner in a small town. Okay, maybe it's like a mining town or something. Okay, we have 6 people in the diner. And we ask, you know, what is your annual income? All right, and then so our 6 people say we got, this guy makes 60,000, another makes 60,000. So they all make 60,000. 3, 4, 5, and we'll say the last person makes 70,000. Okay, maybe. So here, the median would be equal to 60,000 because we got 6 people, and then we would just kind of draw a line there. And our mean, we would add all of these up and divide by 6. We would have 370,000 divided by 6. We would get a mean income of $61,667. Okay, if I round off. All right, let's say I don't know, a rich person walks in, Bill Gates. I have no idea what how much money he makes. Let's say he makes 10 million a year. Okay, and then we copy. So now there's 7 people in the diner, and these are their incomes. Okay. All right, if I were to add all of these up now, okay, our total income would be 10,370,000, and I would divide this by 7, and our average income, our mean income, would be $1,481,429, okay? So, whereas before it might have been fair to say the average income is, you know, a little over $60,000, 61,700, something around there. Does it feel right to say that the average income in this diner is $1.48 million? Yeah, it doesn't feel like it's quite represented. So this is a case where it's extremely skewed, and we can see that the mean is affected by extreme values. Okay? What is the median here? Yeah, so it's actually still 60,000. I should actually move this down to the bottom, okay? And we would arrange these things, and we would say, okay, well, there's 7 values here, and so the median would be, out of these 7 values, this is the median where, you know, once I've lined them up, I've got 3 values that are smaller and 3 values that are larger. So the median is not affected. Median is still 60,000, and it's not affected by extreme values. Okay. But depending on your context or your situation, you may actually want to use this value. You know, if we had to ensure the people in the restaurant against loss of income or something like that, we wouldn't want to buy a policy that just covers everyone for $60,000 a year, okay? Because if something happened to the restaurant or something and everyone inside, then you know, to lose Bill Gates in there, that would be problematic, okay? All right, is that okay? All right, let's talk about some of the measures of dispersion, okay? Well, let me just further talk about the median, okay? So the median, again, is the halfway point. Okay, spot or value where half of the data is larger and half is smaller. Okay, and it's not necessarily larger or smaller. You might have tied values and things like that. So to find the median, okay, arrange your values from least to greatest. Okay, and then you know, count how many values you have. Okay, and then find the spot, find the location where n over 2 values, half of the values, will be smaller than the median. Okay. So if you have an even number of values, so let's say you have 20 values, then the median will be between the 10th and 11th values, okay? So you'll have 10 10 smaller and 10 larger. Okay, so the median is between the 10th and 11th numbers. Okay, let's say you have an odd number of values. So let's say you have 21 values. Okay, you will have 10 smaller, 1 median, 1 equal to the median, and 10 larger. Okay, so in this case, the median is the 11th value. Does that make sense? Okay, so if you have an odd number, you're gonna just, if you have like 51 numbers, okay, you'd say, okay, well 51 divided by 2, that's gonna give me 25.5. So you're gonna have 25 that are smaller than the median, 25 that are larger than the median, and the median itself would be the 26th value there, okay? All right, why don't we take a short break. We'll come back in 5 minutes and we'll talk about spread and all of that other stuff here.